Okay, so make sure you bring up your homework at some point. So this weekend I'm going to a conference, so Bluffton Lab will not meet next Tuesday. We're still gonna have lecture because I have a red eye and I get back early Tuesday morning. And so lab is not gonna happen. But we will have lecture because we can't afford to skip that. People who have lab in Beaufort, that will be as normal for the like 2 of you that are in here. 3, right? 4. Yeah, so we will have Beaufort lab on next Wednesday. Okay.
So does that mean like the lab after is gonna be like both?
No, today is gonna be both days. Today is gonna be both days, but there's some stuff I'm gonna do for you. Just, yeah.
You said no lab.
No lab next Tuesday. Right. Most of the time. Yeah. We're still gonna start at 1:15 because I have my lunch. And you should eat your lunch too, because I don't want anybody passing out in the middle of lab. Okay, let's do chapter 20. What do we like the document cam better or the iPad? This okay, because this is not work. I mean, it's working, but I can't get the HDMI to work, so I guess that's okay. All right. So we did aldehydes and ketones, and now we're just going to take one side of the aldehyde or ketone and replace it with what I'm going to call Z. And in this case, Z is a heteroatom, so not carbon or hydrogen. So if Z was carbon, that would be a ketone. And if Z was hydrogen, that would be an aldehyde. So we're going to do, well, basically everything else that you can put there with some exceptions. And then one of the compounds we'll talk about, well, you'll see, it doesn't look anything like the others, but I'll show you why it sort of is the same. Okay, so we're going to sort from most reactive to least reactive. In the middle, we have, there's going to be 6 things here, so budget your space. In the middle, we have sort of the parent, the actual carboxylic acid. I don't know, let's go to the left first, I guess. The next most reactive is this functional group, which kind of looks like 2 carboxylic acids stuck together. And this is an acid anhydride. Anhydride? Moderately. Acetic anhydride? Kind of, it's expensive to transport though, because it's a hazmat. Yeah. Speaking of reactive, expensive, and expensive to transport, the most reactive member of this family is the acid halide. Here, X is a halogen, but in all cases that we're going to talk about, X is going to be chlorine. So those are going to be acid chlorides. You can make acid bromides and acid iodides, I suppose, but nobody really ever does that. Acid chlorides are the most common. Okay, so those two are more reactive than the parent, carboxylic acid. And then we go in the other direction. This one, hopefully we've seen before. We also are making one of these in lab, either this morning or this afternoon or tomorrow. That's an ester. Esters are fun because they usually smell nice, right? Wintergreen? Yeah, okay. Very similar to esters are amides, and amides just have nitrogen instead of oxygen. I've drawn it with hydrogens here in H2, but it can actually be in R2, or there can be other stuff attached to that. That's an amide. And then the weird member of the family, the nitrile, looks like that. And clearly it's different than all the rest of them because we don't have a carbonyl. And you would think that would make its reactivity significantly different from all the others, but in fact, it's only just a little bit different. And the reason for that is, well, in all of these cases, we've got a carbon-oxygen double bond that's polarized toward the oxygen. And so the carbon is electrophilic because it's electron poor. And in a nitrile, the same thing happens. The nitrogen pulls more electron density toward itself. And so just like the carbonyl carbon in all of these carbonyl derivatives, the carbon at the middle of the nitrile is electrophilic, and it's not a carbonyl carbon, but it kind of plays one on TV. Okay. Instead of starting with the parent with carboxylic acids, which would seem logical and is logical, we're going to go from most reactive to least reactive. So we're going to start talking about the really reactive compounds. And the reason for that is it's easiest to make a less reactive compound from a more reactive compound. So if you're trying to figure out how to synthesize any one of these molecules, it's best if you can to try and start further on the left rather than take an amide and try to make an acid anhydride from it. That's going to be more difficult than turning an acid anhydride into an amide. Okay, so that means we're going to start with acid halides or acid chlorides. Okay, so acid halides are also called acyl halides. Whatever. So the way I'm going to organize, we're going to do a little mini section on each of these functional groups. The way I'm going to organize it is first we're going to talk about the synthesis of this functional group, so how to make this type of compound. And then separately, we'll talk about reactions of each of these functional groups. So, sorry, let me go back to this. You're going to find I'm going to start repeating myself a lot in this chapter. And that's because, well, there's one way to go from an acid halide to a carboxylic acid. And there's also a way to go from a carboxylic acid to an acid halide. So that sort of counts as a reaction of both of them, but just going in different directions. It'll make sense when we talk about it a little bit more. And speaking of, let's talk about that reaction because it's the first one we need to mention. So how do we make acid halides, which, as a reminder, are this, an acid chloride. Okay, that's all we're going to talk about. So here we need to start from usually a carboxylic acid. And we're going to use a new reagent you probably haven't seen before, and that is SOCl2. This is thionyl chloride. I previously said that we need to make a less reactive compound from a more reactive compound. And so I'm saying, okay, we can use this reagent to go from carboxylic acid to the acid chloride. But that means we're going in the opposite direction because the chloride is more reactive. And that's because thionyl chloride is an even more reactive compound than the acid chloride that we're trying to make. So pretty nasty. We're not going to use it. But it gets the job done. Okay, as side products from this reaction, we get sulfur dioxide gas and hydrogen chloride. So generally kind of a nasty reaction to have to do, but a lot of times you need that strong reactivity that comes from the acid chloride. Okay, reactions of acid halides. The first is kind of unfortunate that it happens, but it's hydrolysis. So we've gone through all this work to make our acid chloride. We've used this fancy reagent and everything. And oops, we left our stuff open to the air for too long, and some of the humidity from the air got into the flask. Oops, we get our carboxylic acid starting material back. So if you let acid halides get wet, or, I mean, you can't expose them to the air, but they do hydrolyze pretty quickly back into the carboxylic acid.
So he did this, we have to do it like in like
Yes, but not for, well, mostly because they singe the back of your throat and all this stuff. They're horrible to work with. But for this hydrolysis part, you would just try and work with it quickly and keep it closed as much as possible for multiple reasons. But partially to keep it away from water. Yeah. Okay. So this is a problem because we're using water as a reagent, which a lot of times if there's water in there, that's going to happen. So we get an OH on our molecule from the water, but we can take the same kind of reaction and make it useful. Instead of doing hydrolysis, we do alcoholysis. A lot of lysis words today. And this is really the same reaction, but instead of water, we replace one of the hydrogens on the water with an alkyl group of some sort, or any sort of organic molecule. So that's an alcohol. And additionally, we want a little bit of pyridine, and that's going to act to absorb some of the acid that's produced in the reaction, so it doesn't affect the product. And we get an ester. Okay, so finally, this is actually kind of useful because rather than just destroying our acid chloride that we worked so hard for, we can now use it to make an ester. Okay, so as an example, if we take this acid chloride, that's acetyl chloride, and we treat it with this alcohol, and have some pyridine in there as well. Well, what are we going to do? The chlorine's going to go away as HCl, and we're going to make a bond between the R group, or rather the oxygen that's attached to the R group, but so that R group is going to end up on the ester. Okay, so what we should probably do is redraw one of our starting materials, the acid chloride, and the chlorine is going to get replaced with an oxygen. And well, all we need now for the S to make the ester is the R prime group, which is just the organic molecule that's attached to the alcohol. So here's our alcohol. And so the R prime is going to be that. So all we have to do is put that group on there, and that is our product, ester. Additionally, and this isn't an incredibly synthetically useful reaction, but we'll mention it, is if you take an acid chloride and you treat it with an amine of some kind, aminolysis, here I'm just going to use ammonia, then we get an amide. And as a side product, ammonium chloride. So that has to, this is related to the fact that we used two equivalents of NH3. So only one of them actually goes into the target molecule, right? Replaces the chlorine. So there's one of the nitrogens. The other nitrogen basically serves to soak up the HCl that's produced in that reaction. So anyway, we go from acid chloride to amide. Okay, and finally, another reaction we can do is we can use Grignard reagents. And in fact, you can add a Grignard reagent to, well, any of the types of molecules we're going to talk about, and it'll do a reaction of some sort. Let's try that again. Okay, so in this case, I'm actually going to add an excess of Grignard reagent rather than just one equivalent. So what this is going to do is we're going to make a tertiary alcohol like we would expect if we started with a ketone or something like that. But notably, we have two of these R prime groups that were originally on the Grignard reagent. So say if you wanted to just add one alpha group and make a secondary alcohol or something like that, you cannot do that directly from an acid chloride. It would be kind of useful if you could, but the acid chloride is so reactive that it's just going to gobble up as much of the Grignard reagent as it possibly can. Okay, questions on acid halides. So as you're sort of building up a library of reactions, one thing you should certainly look for is trying to be able to decide if you have multiple functional groups, what's going to react first. And it's going to follow this order, right? So if you have a molecule and you see it's got an acid halide, that's the first thing you should look at. Then if it has an acid anhydride, then if it has a carboxylic acid, and so on and so forth. So if any of these reactions can happen, given the reagents and the starting materials that you have, these are the reactions that are going to happen. And as we continue through the chapter, the things that occur are going to become a little bit less likely to happen. In other words, if you've got competition between two groups for which one's going to react, the one toward the left is going to react. Yes.
So, it's least reactive concentration.
Mhm.
Just. Is that why like people use nitrile gloves instead of like latex?
Yes. Indirectly, yes. It's some polymer. I don't remember exactly what it's made of, but okay, cool. So that's acid halides. Okay, acid anhydrides. So as a reminder, these are this kind of thing. Now you might imagine that you could make this sort of molecule maybe by taking a carboxylic acid and removing water from it, right? Anhydride, so remove water. Okay. So if we have, let's say we actually have two equivalents. If we remove water, okay, well, we get rid of OH and H. That gets rid of H2O. Okay, and now we just kind of attach those two. This is not a mechanism. I'm just kind of showing you where the molecule comes from. We would get something like this. It's our acid anhydride. The problem with this is it requires extreme heat. For acetic acid going to acetic anhydride, you need 800 degrees Celsius. So that is not practical. What is more practical is to start from a more reactive molecule, right? In this case, we're going from carboxylic acids to a more reactive functional group. That's why we need a stupid amount of heat to do it. But let's start with a more reactive functional group than acid anhydrides, which is an acid chloride. So we know how to make that. So we'll say we already have this molecule. Now what we need is, rather than a carboxylic acid, we're actually going to use carboxylate salt. So this is just a carboxylic acid that's been neutralized with like sodium hydroxide or something like that. We'll talk about acid-base reactions of carboxylic acids in a bit. But we take this anion and we do essentially a substitution reaction. It doesn't follow like an SN2 mechanism, but we're not going to talk about the mechanism of this. And so actually, let me make this R prime. And there's our anhydride. So this can be done at room temperature. Can't do it in water because you have that acid chloride that would get destroyed by water. But in general, that's a much more reasonable reaction conditions to use. Okay, the classic reaction to do with an acid anhydride is acylation. So if we take acetic anhydride, or any anhydride, but acetic anhydride is by far the most common. And we treat it with an alcohol. Of course, you could draw this the other way. You could start with the alcohol and use acetic anhydride as a reagent, as we have done previously in lab. And from here, you'll get an ester. This is a classic way to make an ester, specifically an acetic ester that's got, this group here. By the way, we sometimes abbreviate acetic anhydride as AC2O. It's got an oxygen atom with two acetyl groups attached to it. We can also do a very similar acylation reaction with an amine. And that still adds our acetyl group, but instead the bond is to the nitrogen that used to be part of the amine, and we've still got our R substituent on the nitrogen atom. And so we've made this functional group, which is an amide. So this is actually a secondary amide because it's got an R group on it. Now, by far the most common is with the alcohol on top. And we have seen this before. When we did the synthesis of aspirin. So in that reaction, we started with salicylic acid. Now I've got two functional groups here, an alcohol and a carboxylic acid. And we treated that with acetic anhydride, AC2O. And we got aspirin. Okay, so we have our anhydride here, and we have an alcohol. So we're going to still have our oxygen atom right there. But on the other side, we're going to have the acetyl group. So part of the half of the acetic anhydride molecule ends up on the alcohol. Of course, you could also look at it from the other direction. You could say, okay, if we start with acetic anhydride and we add salicylic acid to it, this is going to end up looking just like the example. So if we do this sort of thing, just flipping the two reagents, now we can look at it from the opposite direction. We can say, okay, so we're going to start with half of the acetic anhydride molecule, and to that we add whatever was attached to the alcohol. In this case, it's all of this business that was attached to the alcohol of the salicylic acid. So R, 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 like that. If there's anything you should remember about acid anhydrides, that is that they're symmetrical, right? I mean, you could have different substituents on either side. It's certainly less common than having something like acetic anhydride where it is symmetrical. But whenever this does a reaction, it's going to split in half. Okay, questions on acid anhydrides? Okay, so the last little section that we'll talk about today is the parent carboxylic acids. Okay, we have a couple more things in this case that we will go into just because this is kind of the parent chain. So first, let's briefly talk about nomenclature. I'm not gonna like make you name them or anything. I just want you to have seen this. So the suffix for carboxylic acids is oic acid. Convenient that acid is in the name, so it's kind of going to give you the answer, at least to what sort of functional group you might be looking at. So no, that is not a carboxylic acid. That is. There we go. So in this case, our parent carbon chain, 1, 2, 3, 4, is butane. And so that becomes butanoic acid, but this has a common name. Butyric acid. Same root word as butter. That's where the BUT comes from. So this is a component of butter, cheese. I think goats emit a lot of this, and so it has been described as a goaty smell, but probably most noticeably, it's the smell of vomit. No offense to the goats, but you know. All right, so butyric acid, not particularly fun to be around. Have you ever gotten like butter? I don't know, but okay, so whenever you eat pizza, you know how you get like stuff on your lip because you know it's kind of a messy food, right? I don't know about you, but I always go like that after I eat pizza, and it smells like like throw up, kind of. No? Am I crazy? I mean, well, I don't know what kind of pizza y'all eat, but anyway, yeah, so it's sort of, I don't know, it's interesting how chemicals smell very different depending on what other stuff they're mixed with and also the concentration. So I'm in like I assume in low concentrations this would smell like butter, sort of milky, but then if it's a lot of it, then it's just the I guess, yeah, I don't know. Honestly, that fridge, the fridge isn't too bad. You should just smell our fridge in my research lab. That was really bad.
Well, it's like. That part.
Okay, so this one is formic acid. And I know I said that all of the carboxylic acids and derivatives had to have an R group on the left side. on the left side, but the way I was drawing it on the left side. And this has a hydrogen, so okay, it doesn't technically count, I guess, but it's still called a carboxylic acid. Do any of the wonderful bio people in here know what formica is in taxonomy? Ants. I've heard it's a family or group or a clade or whatever, I don't know. But this is what makes ant bites sting, formic acid. So from the name formica for ants comes formic acid, and then really a lot of different things that just have one carbon in them. So formaldehyde, the name for formaldehyde comes from the name for ants. Anyway. I miss not having ants. When I was in Nevada, there were no ants.
There are invasive species that are disturbed. How about mosquitoes?
No mosquitoes, no bugs at all. It was so wonderful. Okay, acetic acid, we should know this one. This is vinegar. Although fortunately for us, cooking vinegar has, some salts and flavorings added to it. And then, I don't know, what is it, 3 to 5% acetic acid in vinegar. So when you have a bottle of acetic acid in the lab, that is like vinegar's mean older brother, and it smells like it too. And then this one, benzoic acid. Make this steal your drink. Yay, sodium benzoate preservative. Okay, so the sodium salt of benzoic acid is a really common food preservative. Common enough that I was correct in my bet that I would find it in her drink. And you might think, okay, well, that means there's no benzoic acid in your drink, but I bet there's like phosphoric acid or some other thing to make it tart in there, and that just causes the sodium salt to convert back to benzoic acid. So anyway, I told you not to drink the lab chemicals, Kyla. Okay. Okay, so some brief things about structure. I'm going to draw this kind of funny. So this is just two carboxylic acids next to each other. One of them's flipped upside down and spun around, but whatever. So because we've got these oxygen atoms with lone pairs, and we've got these hydrogen atoms that are on the end of the acid, we can have really strong hydrogen bonding. Between two carboxylic acid molecules. Now, of course, this occurs in a lot of different other molecules, but carboxylic acids have, well, here I've shown it drawn from the carbonyl oxygen, but it can also hydrogen bond from that sort of alcohol, quote unquote, oxygen, and all sort of in between and everything. And because of that, if you compare acetic acid and ethanol, which are the same molecule, but one is missing a carbonyl group. We look at the boiling points. Ethanol boils at 78 degrees Celsius. Any guesses for acetic acid? Greater, smaller, higher, lower? So we've got an extra oxygen here that can participate in hydrogen bonding. And so that's going to increase the intermolecular forces. IMF, intermolecular forces. And so that means that acetic acid is going to have a higher boiling point, and it does. It's about 118. This is just trivia, but I want to show you that the hydrogen bonding here is really important. And for example, this is what makes carboxylic acids more often than other compounds soluble in water. So formic acid is soluble in water. Acetic acid is, well, it's vinegar, so it better be soluble in water. Benzoic acid, it's got this huge benzene ring on it, right? That's larger than the whole rest of the molecule. And you might think, okay, that benzene ring is really nonpolar, and so benzoic acid shouldn't be soluble in water, and it's not at room temperature, but as soon as you heat it up, it dissolves. So that solubility in water, at least at high temperatures, is also due to hydrogen bonding. Okay, we haven't really mentioned this, but okay, they're carboxylic acids, so they better be acidic, and they are. So if we take acetic acid and let's say we treat it with some sort of base, so maybe sodium hydroxide. We can deprotonate the acidic hydrogen with our hydroxide. And those electrons go onto that oxygen atom. So if we start with acetic acid, the salt that gets, oh, there we go. The salt that gets formed is sodium acetate. Sodium benzoate, sodium acetate. Okay, that's fantastic. But Dr. Eubanks, can't you just do the same thing with ethanol? And you can draw it, so I'll be good and draw my lone pairs. Okay. So you can draw the same thing with ethanol to make that, which again looks similar to the sodium acetate, just without the carbonyl group. But the problem here is there's no resonance stabilization, at least referring to the negative charge. At least in ethanol. So in ethanol, the negative charge is sat there on the oxygen, and it doesn't really have anywhere to go. It doesn't have anything else to share that electron density with. And because of that, you actually can't use sodium hydroxide or a hydroxide base to deprotonate ethanol. That reaction doesn't work. But you can do it with carboxylic acid like acetic acid. Definitely alluded to this, but why are carboxylic acids so acidic? Well, if you take this reaction, we add base and we remove a proton. So same reaction I just showed before, except without the arrows. We get to that ion. But, and this is the crucial part, we can draw a resonance structure of that ion where we distribute the negative charge. So we can form carbon oxygen double bond there, and we can have these electrons move up onto that oxygen. So what do we get then? Well, we can now have a double bond to the oxygen there. Now we've got a single bond to the oxygen on the top, which has 3 lone pairs and a negative charge. And you might say, well, that's the same molecule. And it is the same molecule because we've got a methyl group attached to a carbon with 4 bonds, methyl group attached to a carbon with 4 bonds. One of them is an O-, and one of them is a carbonyl. So it's the same molecule, but it's still a valid resonance structure because we've actually moved the electrons around. So if we want, we could draw a structure that kind of better indicates the delocalization, if you like, or the distribution of that negative charge to those 2 different places. And so we can do that, for example, by drawing this sort of dotted line. It's kind of visible. That dotted line showing that both of these bonds to the oxygen have some double bond character and some single bond character. And then to indicate the charge, well, the charge is sort of on the top oxygen and sort of on the bottom oxygen. So we kind of just draw it out here in the middle of nowhere. And so that doesn't really, you couldn't draw a mechanism with that representation, but it does show you that the deprotonated form of a carboxylic acid really has the negative charge spread over a wide area. So charge, distribution, stability, and here I'm talking about the conjugate base, which is that. So stability means lower in energy, and so that means the proton is more acidic, more likely to come off of the molecule, because if we do lose the hydrogen atom, the proton, then we've got this still pretty stable, delocalized carboxylate. So this is carboxylate with delocalized electrons, and that's more stable than, say, our deprotonated ethanol example from up there, which has none of that interesting stuff going on. So that's why carboxylic acids are as acidic as they are. Okay, speaking of acidity, I've told you that carboxylic acids are acidic, but how acidic? So if we say that carboxylic acids are kind of in the middle here, they are intermediate in between, well, the vast majority of organic compounds. For example, alkanes or alcohols or ketones or anything like that. Those are not particularly acidic. Here, the ethanol is the most acidic, but still not by very much. And so as a point of comparison, the pKa, where lower pKa is something that's more acidic. Ethanol is roughly 16. A carboxylic acid is 4 to 5. And this is on a logarithmic scale, so that's like 10 orders of magnitude, which is, I don't know, bazillions. So carboxylic acids are bazillions of times, that's a scientific term, stronger than something like ethanol, just because of that resonance that I showed. So it's a huge difference. But there's almost an equally large jump between carboxylic acids and inorganic, or sometimes we call them mineral acids. And so that would be stuff like HCl, sulfuric acid, nitric acid, etc. And these have pKa's less than 0. So that's at least another 1,000,000 times stronger than carboxylic acids. You don't need to know these numbers or anything, but I do want you to realize that there's a massive difference in acidity between regular organic compounds, carboxylic acids, and inorganic acids. Okay, that actually gets us about halfway through the chapter. So we're going to pause there, finish up the rest of the stuff on, is it Tuesdays? I don't even know what day it is. Finish up everything else on Thursday, hopefully, and then we'll have Tuesday for some practice. All right, see you in lab. Make sure you eat lunch. No, we have another chapter.